So we are discussing discrete Fourier transform, okay, discrete time Fourier transform actually. So some property you can see in the slide that if you shift the time domain signal, okay, time shifting property, you shift the time domain signal x of n by k amount. In frequency domain, it is multiplied with e to the power minus j omega k with the x omega, that is the Fourier transform of the original signal xn, unshifted signal x of n. Similarly, time reversal is if you reverse the time x of uh, changes to minus n, then x of n is Fourier transform is x of minus omega. Okay. Then other important property like correlation. Correlation is what? It is the convolution between one normal signal and another folded signal. Folded signal is xt of minus L. Okay. Where convolution is xt of L. Convolution in the formula of convolution, it is just reversed. X2 of minus L. If we take correlation. Then frequency shifting. As you have seen in time shifting, that if you shift the signal in time domain, okay, similarly you can shift the signal in frequency domain by omega 0, x of omega 1 minus omega 0. Then in time domain, its effect is seen as it is multiplied with e to the power j omega 0, okay, n. So here some difference is that here it is minus omega 0 in frequency domain. So in time domain it is multiplied with e to the power plus j omega 0 n. Whereas in time domain, if you shift it by k unit, in frequency domain it is multiplied with e to the power minus j omega, okay, not plus j omega k. So that is the difference. Now there are some topics I just briefly go through it. That what is the relation between Fourier transform to the Z transform? Fourier transform to the Z transform. You know that Z transform is what? X of summation x of n into z to the power minus n. Okay? That is the Z transform. Whereas in Fourier transform, it is summation x of n into e to the power minus j omega n. So just difference in e to the power minus j omega, just difference in the term that is multiplied with x of n. In Fourier domain, Fourier transform, it is x of n is multiplied with e to the power minus j omega n, and in Z transform it is multiplied with z to the power minus n. So we can correlate z with e to the power term. So that means for j omega. Now that means what? Z actually is a complex number, and it is defined as z is equal to r into e to the power j omega. So here we put r is equal to 1. So we get z is equal to e to the power j omega. So r is equal to 1 means what? Can anybody tell? R is means what? R is equal to 1 means what? R is what? Can anybody tell?
Sir, the radius of unit circle.
Yes, radius of the unit circle. So that means uh, Fourier transform. Here you see the graph that therefore the Fourier transform can be viewed as the Z transform of the sequence evaluated on the unit circle. Okay. Z is equal to the power j omega. So mod z is equal to 1. Magnitude r is what is the magnitude, that r is equal to 1. So if uh, since xz has some ROC, region of convergence, so the unit circle should be included in the ROC. Okay? The unit circle should be included in the ROC. Then only its Fourier transform is valid, will exist. Otherwise not. Then another topic, that is what is the relation between Laplace transform and Z transform. Okay? So just you go through the its equation, that how we define Laplace transform. Laplace transform is what? It is defined for continuous signal. Okay? And it is defined as x of t e to the power minus t. Okay? But this x of t is continuous signal. We cannot use it as discrete signal. But if we want to use it as discrete signal, then we should represent it as quantized form. Okay? That is x cubed of t. So that x cubed of t is actually the sampled version of xt, or written as the sum of xn into delta t minus nt. Okay? Delta t is the impulse function located at t is equal to 0, and there this is weighted by the sample, the magnitude at that point n is equal to 0, and if you delay that signal, okay, impulse function, and take the samples at corresponding locations, then we can represent that sample person. Independent variables, independent. In a case like wave equation in physics space, independent variables. So this way we can represent the signal. Now take the integration into the summation, interchange the order. So that means that it becomes delta t minus nt to the power minus st dt actually is 1 when t is equal to nt. T is equal to nt, that time that exists. Yes, otherwise it is 0. So you put t is equal to nt over there. So this whole integration becomes e to the power minus nst. So now you can resemble these two with z transform, that z to the power minus n, provided z is equal to e to the power st. So the z transform will be equal to Laplace transform if z is equal to e to the power st, whereas Fourier z transform will be equal to Fourier transform if z is equal to e to the power j omega. These are the two conditions. Now what is the implication, that you can see in the comparing the S plane with Z plane. S plane with Z plane. Okay. So what is S plane? S plane is what? S can be written as sigma plus j omega. Okay. So Z is equal to e to the power st. That means in place of S we write sigma plus j omega. Okay. Sigma plus j omega, that means e to the power sigma t into e to the power j omega t. Okay. So this representation of Z actually can be compared with uh, frequency variable omega is there, capital omega, and magnitude. So real magnitude and phase part. Okay. So angle part. So magnitude is e to the power omega t, sigma t, and phase part is j omega t. So if sigma is less than 0, okay, that means the left sigma less than 0 means that is if you see the S plane, that is sigma less than 0 means left half S plane, okay? Left half S plane if sigma is 0. Sigma is less than 0. So that means magnitude is less than 1. Okay. So magnitude of Z is less than 1 if sigma is less than 0. So that means that corresponds to the points inside of unit circle. Okay. This is the unit circle. Okay. And all the points that are present in the S plane are mapped to the area inside the unit circle of the Z plane. Similarly, if sigma is greater than 0, if sigma is greater than 0, so that means sigma is greater than 0. So here uh, mod z would be what? Mod z is greater than S lies on the right side of the S plane. So mod z is greater than 1. Okay. And z lies outside the unit circle of Z plane. Okay. So in this equation, sigma is greater than 0. That means positive. Okay. Sigma is greater than 0. That means positive. Okay. So some value, anything that is having e, value of e is generally 2. Okay. So 2 2 in between 2 to 3. So that means the mod of z is greater than 1. Whereas sigma less than 0, that is negative. So that means 1 by 2 to the power term should be there. 1 by 2 to the power something. So that is less than 1. Okay. But in positive z, a positive sigma, that means mod z greater than 1. So that is the S plane points in the right hand side, it maps outside the unit circle. And when sigma is equal to 0, that means what? Sigma is 0, that means S is equal to only j omega, that is the imaginary axis. Imaginary axis. So that means its magnitude, sigma is equal to 0, that means mod z is equal to 1. So that means on the unit circle. So imaginary plane, imaginary axis j omega are mapped on the unit circle, on the perimeter of the unit circle. Okay. So this is the relation. So is it clear? Please respond, anybody? There are people, lakhs of people, or 99%. They are all people. I have got anybody else? Vivek? That is why I take so much pain. Vivek Kaushal? Ankita?
Yes, sir.
Is it clear? Relation between jet plane, jet plane and S plane. Is it clear? These concepts will be used in other modules. Okay. There are three cases: left half S plane, right half S plane, and imaginary axis. Left half S-planes are mapped into the within the unit circle. Right half S-planes are mapped outside the unit circle, and G omega axis is mapped on the unit circle. Okay. Is it clear how it is mapping?
Yes, sir.
Okay. Then we go to the topic related to Fourier transform, that is discrete Fourier transform. Okay. Earlier we have studied discrete time Fourier transform. Okay. Discrete time Fourier transform is what? It is, let us see the diagram. Yes. Let us consider this example that we took one aperiodic signal, okay, whose Fourier transform was continuous function of frequency. Okay. Continuous function of frequency, and it is periodic over 0 to 2 pi. After that it is repeating. Okay. That was discrete time Fourier transform, and its definition was was minus infinity to infinity. Okay. Minus infinity to infinity x of n e to the power minus j omega n. That is the Fourier discrete time Fourier transform. Okay. Where we took the input signals range from any values. Okay. So what we have seen that now that kind of continuous signal, continuous the representation, that discrete time Fourier transform in frequency domain, that is x omega, actually it is not a computationally convenient representation of the sequence xn, since x of omega is a continuous function of frequency. Therefore, we need to represent x of n by sample of its spectrum x omega. Such representation leads to DFT, discrete Fourier transform. Okay. So the DTFT gives you the frequency domain representation of discrete signal over continuous frequency range. Okay, over the continuous function of frequency omega, and they are repeating after frequency 2 pi. That means harmonics are present. Okay. So why not we take only the samples, okay, over the range 2 pi. Okay. Then you can represent it. So let us simply represent. So you see the diagram. Okay. It will be clear. X omega is the DTFT. Okay. DTFT of x of n is equal to minus infinity to infinity e to the power minus j omega n. This is the Fourier transform of the discrete signal, and it is the DTFT. Okay, and we get the Fourier transform DTFT as the continuous function of frequency, not discrete. And they are repeating after frequency 2 pi, 0 to 2 pi. At 2 pi again it is becoming same. So if we want to represent it in a convenient way, so we can sample it, okay, at some discrete frequencies which are spaced by delta omega. Okay, delta omega. Now, and say we take n number of samples within 2 pi. n number of samples. Within 0 to 2 pi frequency, we sample it at interval delta omega, which is equal to 2 pi by n. We take n number within range 0 to 2 pi. So the first samples will lie at 2 pi by n, 2 pi by n, first samples. Second sample will lie at 2 into 2 pi by n. The interval is 2 pi n because the range is 2 pi divided by n. 2 pi divided by number of points that we are interested, that is number of points is capital N. So it is 2 pi by n. So first sample exists as 2 pi by n. Second sample exists at 2 into 2 pi by n, like that. So there exists one sample, that is kth sample, that exists as k omega is equal to k into 2 pi by n. Okay. So you can see that the samples just before the samples at 2 pi is n minus 1 2 pi by n. Okay. And this is n into 2 pi by n, that is 2 pi. Okay. So this, after that, it is the next cycle. So we take only these samples at some discrete points of the frequency domain representation of the original signal xn. Okay. So first we took the sample signal, then we take the Fourier DTFT, then we again sample it in the frequency domain, we get DFT. Okay. Now what is the mathematical implication? So we take the samples, discrete samples at 2 pi n by k, any random or arbitrary samples at k. So it is, say, k into 2 pi by n. So 2 pi by n into k. So we just put the frequency omega 2 pi k by n at that corresponding value. So its magnitude is to the power minus j 2 pi k n by n. So in place of omega, in this equation, in place of omega, we write these samples 2 pi k by n into k. And here also 2 pi by n into k. Okay. Now this is, this whole this whole series is written slightly different way, that we since it is a continuous range, n is equal to minus infinity to infinity. Okay, just we subdivide into some equal range of frequencies, that is that is spanned for only n number of points. So let us say at the middle we take the points from 0 to n minus 1. Okay. We divide it, the whole continuous range, within some small divisions, and each divisions range from with each divisions having points, having n number of points. Okay. So the central division is having range 0 to n minus 1. The previous division is just minus into minus 1. And after that, after this, it's n to n plus 1. Okay. N to n minus 1. N plus n minus 1. N to, since n number of points are there, so it is starting from n. So n plus n minus 1. So it is 2n minus 1. So like that, it ranges over the continuous range. Now, the whole range is represented in the mathematically as L is equal to minus infinity to infinity over another summation, that n is equal to ln to ln plus n minus 1, and this term remains same, x of n e to the power minus j 2 pi k n by n. And this, the outer summation, actually represents the variation of L minus infinity to infinity. Okay. So this single summation is represented into double summation. Single summation is represented to double summations, taking repetition of some representing repetition of some finite number of points. Okay? So here again we write that we let us take that we take the this outer summation inside of that, okay, inside of that, or changing the order of the summation. And here how we are writing that we represent uh, n, okay, n tends to so for n, when n tends to ln, okay, when n tends to ln, then uh, the outer say that n tends to n l minus 1. We just changing the index, okay, changing the index of n to n minus ln. Okay, here n index is changed to n minus ln. Now we put the limit. If n tends to ln, then the n tends to 0, and if n tends to ln plus n minus 1, okay, that is the outer the extreme, the limit, last limit, okay, upper limit is ln plus n minus 1. So if n tends to that, then n tends to n minus 1. So this is written by writing this summation, by changing the order of the summation. This goes to inside, this goes outside. So when this goes outside, then we change the limit as this way. So this becomes 0 to n minus 1, and limit of L remains same. And we, if we keep n minus ln, n as n minus ln, so here also the exponential term, in the exponential term, it becomes n minus ln. So this becomes 1 unity. Okay, this part remains same and the last part remains unity. N cancel out, so it remains 1. So it does not change much. So now focus on this part, focus on this summation. Okay, this is what, this is your, this includes the time domain signal xn, okay, which was discrete signal, okay, and aperiodic, okay, and it is repeating. Okay, so you are taking, we are just repeating, okay, over periods, the points we take n, the capital N, okay, and they are repeating. Okay. So like we here graphically it is shown that if your original signal is x of n only contains 4 points, so just delay by 1 unit. Okay. So it becomes a delay by n unit, it becomes x of n minus n. Okay. And if you then add these two, xn plus xn minus n, if you add, then it becomes this. Similarly, x of n minus 2n, it is delayed by another 2n terms. So all these are added. Okay. So it is actually the graphically it is shown that xn, the aperiodic signal has become now periodic. Okay. Aperiodic signal xn is now periodic if you take the sum. Okay. So if this is periodic signal, okay, so we can apply the Fourier series Fourier series concept. Okay. So Fourier series is, so it is a periodic signal, we can say, okay, although it is generated from your original signal x of n. So if you apply the rules of Fourier series, okay, it's slightly hazy, but you can unsee it. Fourier series, then periodic signal. So according to the formula for Fourier series, Ck is the coefficient, and Ck is Fourier coefficient is represented by this. Okay, and uh, here, so we can compare this one, okay, this equation, okay, with this equation, okay, xpn. So this is actually xpn. So if you compare this, we can write x. This is actually x of right hand side, x of 2 pi k by n. Okay, this part x of 2 pi k by n, and this is xpn. Okay, xpn is this one. So and this is equal to nck. So this means what? Ck is equal to 1 by n into x of 2 pi k by n, or this Ck is actually what? Uh, Here you can write that xpn in place of x of 2 pi k, here xpn is what? Xpn is this one. So in place of Ck, we write again this one. In place of Ck, here we write this one. So this relations, actually it is what? Representation of the periodic signal. Xpn is the periodic signal whose actually it is represented in terms of Fourier series. Okay. And so this relationship provides the representation of the periodic signal xpn from the samples of the spectrum x of omega. So what we took, that we initially took the DTFT, of this is x of omega. Okay, we sampled it, and after sampling, okay, we represent it in terms of Fourier series. Okay, so here. Uh, so this we can say we can recover this x of omega, okay, or x of n from the samples. So but there is a condition that what should be the relationship between xpn and x of n. Okay. So that is given here, that earlier we have considered that x of n, okay, x of n was of finite length. Okay, and this one, okay, L number of points. So it was now repeated. Okay, so we see that what we finally understand, that we, after sampling the frequency domain signal, okay, frequency domain signal, and again uh, taking that samples, okay, taking that samples, we take the inverse uh, Fourier transform representation. In inverse Fourier transform representation, we see it is actually the Fourier transform of a periodic signal. Okay, although it came from the periodic signal, we come to the conclusion that it is actually representing a periodic signal. Its inverse Fourier transform represents one periodic signal. Now this periodic signal, whether is similar to your original discrete signal or not. So to have that, to accomplish that, we have to find the relation between the periodic signal and xn. Okay, so xn is having certain durations, xpn is having certain durations, so there should be some matching between these two relations. So let us say that x of n is having length L, okay, and that xpn and x of the xpn and this your reconstructed signal. Reconstructed means what? Reconstructed from the in taking the inverse Fourier transform of your sampled samples of the Fourier domain signal. So so there must be some aliasing that the length of the two, that is time domain signal, is n, and after reconstruction we get n number of points, so n should be greater than L. Okay, n should be greater than L. That L is your length of the original signal and n is your length of the reconstructed signal. Reconstructed means after that periodic signal that is coming from Fourier series representation, okay, of this summation that you have seen discussed. Okay. So if n is greater than L, then there will be no aliasing. If n is less than L, then there will be aliasing. So x of n would be equal to x of pn, that is reconstructed signal, if n is greater than equal to L. Okay. So finally, what we conclude, that just go through these points, this discussion. Finally, what we summary, what we see, the Fourier transform, that if xn is limited to L number of points, L number of points, so x of omega is the Fourier domain representation is n is equal to 0 to L minus 1 x of n e to the power minus j omega n. Okay, that is the not infinity. Okay, that is for these durations only. And when we sample x of omega at omega k is equal to 2 pi k by n, these frequencies, okay, where n is greater than equal to L, that is n is the number of points that we use to sample the frequency domain signal of xn, and L is the number of points of the original signal. If n is greater than equal to L, the samples are xk is equal to x of 2 pi k by n. This should be similar, and we represent x of n. We represent the Fourier transform, discrete Fourier transform, as x of n e to the power minus j 2 pi in place of omega. Here omega would not be used in discrete Fourier transform. It is the sampled value 2 pi k n by n. That is the important thing. Okay, that is the difference. So this is actually your discrete Fourier transform. Okay, this is the formula. Discrete Fourier transform, that x of k is equal to 0 to L minus 1 x of n e to the power minus j 2 pi k n by n, or simply this one xk is 0 to n minus 1 x of n e to the power minus j 2 pi k n by n. Okay, so this is called discrete Fourier transform. Okay, let me underline this. Or this is called endpoint DFT. So after a lot of calculations, we get this DFT, and how it is different from DTFT is that DTFT ranges over continuous range of frequencies, whereas DFT ranges for discrete values of frequencies. Okay, which is the formula? Formula is what? This is the formula. Okay, formula for DFT. So this is the formula for DFT. Okay, and the formula for IDFT, that is inverse Fourier transform, is this one. Okay. So if you know xk is the Fourier DFT representation of xn, whereas x of n, if you know xk, then you can find the inverse DFT, okay, as x of n. Okay, so this thing you need to know, and other details that you mathematically is explained here, you can easily understand. Okay, you just go through it. So actually it is coming from reconstruction of the periodic signal. Okay, so now we just you go through this. Okay, and if you have any doubt, you can ask in between. So do you have any doubt?
No, sir.
Okay. Anybody else? Okay. So now I stop here. We'll meet in the next class. You can leave now.
Thank you, sir.
Okay.